Welcome to the Next Generation Science Standards Toolkit. This module is designed for building and district level administrators. The purpose of this session is to help you develop a basic understanding of the structure of the Next Generation Science Standards, explore the shifts in instructional practice prescribed by the NGSS. How will our classrooms look different now? Investigate resources available to help with these changes, and plan next steps for your school or district. Before we get started, I'd like to share this quote with you. Traditional science laboratory activities are structured around the laboratory report format. Students are expected to engage in a format that outlines the hypothesis, procedures, observations, results, and discussion. Unfortunately, scientists use this format not in the laboratory, but primarily to report their work in journals for publication. In the lab, they pose questions, make claims, gather evidence, debate with each other, compare their answers with others in the field, and attempt to look for patterns across their results. Scientists are engaged in argumentation. At the very core of science activity is scientific argument. Having completed this process of argument, scientists then prepare their written reports for publication. According to this quote, how do scientists learn science? And does this match the typical learning experience we provide in the classroom? Pause the video for a moment while you and your group discuss this question. Another way of saying this is that orchestra students are musicians, students on the basketball team are athletes, and what opportunities do our science students have to be scientists? Please pause the video as you consider this question with your group. In 2011, a framework for K-12 science education was published. This framework is based on a rich and growing body of research on teaching and learning in science and has provided the foundation for the Next Generation Science Standards. Now I'd like to take a look at one of the NGSS standards documents together. Please find the MS, Waves and Electromagnetic Radiation handout. There's a separate module that reviews the details of reading the standards, but I'd like to take a few moments to look at the general structure. Grab a partner and examine the document together. What do you notice? What do you wonder? Please pause the video as you complete this activity. One thing you may have noticed is a colored area in the center of the document. These three colors represent the three dimensions of the framework: the science and engineering practices, or the things students do in the classroom as they learn science, like planning and conducting an investigation, asking questions, etc. The disciplinary core ideas, or the science content, and the cross-cutting concepts, themes that cross every field of science, like patterns, structure and function, and so on. The NGSS presents these three dimensions together, side by side. This is different from our Michigan content expectations, where our inquiry process expectations were listed at the beginning of the document. This side-by-side presentation conveys the idea that these three dimensions are inextricably woven together during the learning process, like the strands of a rope, and that deeper understanding is possible when all three are taught together. So instead of, teaching the method of doing science at the beginning of a unit, it's taught along with the content. This time, let's focus up here at the top. The NGSS are written as performance expectations. These describe what a student should be able to do at the end of a unit. They're not meant to be lesson sequences or required activities. Teachers, schools, and districts will have to determine what student experiences will lead to these performance expectations. Basically, each performance expectation is like the rope we looked at earlier. The three dimensions are woven together to illustrate how they fit together. One of the most powerful things about the NGSS is that they were written with the Common Core state standards in mind. At the bottom of every page of standards, connections to Common Core state standards in ELA and math are outlined, so that as teachers ask students to read, write, speak, model with mathematics, apply a mathematical concept, etc., they know exactly where students are with those skills and concepts. Here is the URL and a screenshot of the NGSS webpage. There are many resources outlined here that you may find interesting. Later in the session, you'll have time to explore these further. Along with the new standards comes some new terminology. Here is a list of legacy terms along with a new idea or concept that's emerged with the NGSS. Many educators refer to the Common Core in science. The Common Core state standards apply only to ELA and math. One section of the ELA standards supports literacy in science, but there's no science content in the Common Core. The new science standards are called the Next Generation Science Standards. They're similar to the CCSS in that they were developed collaboratively in a state-led process, but they have their own name. When students learn the scientific method in school, they come away with the idea that science is linear and that you have to follow a rigid set of steps every time you set out to investigate the world. In reality, science doesn't work that way. One method does not apply to every situation. Instead, we use the science and engineering practices appropriately for each instance. The inquiry and reflection standards that were included at the beginning of the Michigan content expectations are now reflected in the science and engineering practices. The old Michigan terms, content expectations, benchmarks, GLIC, Husky, will be going away, making room for performance expectations that include the three dimensions: science and engineering practices, disciplinary core ideas, and cross-cutting concept. The Next Generation Science Standards are not really national standards. They were created, just like the Common Core state standards, in a state-led collaborative initiative. And so the term national standards is really not applicable. We don't know much about what's happening with the Michigan Department of Education so far. We anticipate that the State Board of Education will adopt the NGSS in the fall of 2013. After that, we expect information from MDE with respect to what's happening with the MEP and the MME. Until then, it will be difficult for districts in Michigan to begin to shift their curriculum in response to the NGSS. For now, we've been advised to focus our attention on shifting classroom instruction so that it's aligned with the NGSS. Please make sure you check back with the MDE website in order to have up-to-date information. So I guess we have to focus on the practice standards for now. What does that look like? Here are the science and engineering practices. You can read about them in depth in Appendix F, which can be accessed on the NGSS website. These practice standards are all interrelated, and it's almost impossible to consider them one at a time. However, when you examine them as a whole, there are four main areas where we will have to shift our thinking with respect to instruction. These areas are content, experimentation, scientific models, and social interaction. We are going to review each of these shifts in practice together, but first, make sure you have a copy of the NGSS Instructional Practice Alignment Handout so that you can begin to plan for your own school or district. As we review these shifts in instructional practice, keep your own school or district in mind. Use the planning tools provided to consider what your current state of science instructional practice is, and what do you expect your classrooms will look like in 3 years as a result of these new standards? So what's your current state and what's your vision of the future? Let's take a look at the shifts in practice with respect to content first. Here's an example from high school physics. Here's a list of the Michigan high school content expectations that have to do with force and motion. And here is a list of the disciplinary core ideas that have to do with force and motion. I realize you can't read them, but it's important just to see what the list looks like. The Michigan content expectations asked us to teach a curriculum that's a mile wide and an inch deep. Students had to know so many different details and facts. The NGSS has narrowed the content to core ideas, but with the idea that these core ideas are taught along with the other two dimensions, the science and engineering practices and the cross-cutting concepts. The content may have gotten smaller, but that just made room for deeper learning experiences that do a better job of reflecting what scientists do. When you look at the entire NGSS document on force and motion, it's not shorter than the Michigan high school content expectations, but the smaller list of concepts is woven together with the science and engineering practices and cross-cutting concepts. At first glance, it seems as though this change might be easy to implement. Just stop teaching so much content. The problem is that teachers have done such a good job of doing exactly what they were asked to do, teach a mile wide and an inch deep. In order to make that experience as meaningful as possible for their students, teachers made connections for students all across the mile, to the point where it's almost impossible for them to consider teaching one thing without teaching everything. As we make this shift toward teaching less content in a deeper way, we'll need to rewire those connections. So in summary, in a conventional science instruction, the overwhelming focus of instruction and assessment is content mastery. Learning objectives attend to a broad and comprehensive content coverage. With the NGSS, fewer concepts are emphasized, but they're explored in depth. The interrelationship of ideas and cross-cutting concepts are emphasized. Content is put to use to generate and investigate questions or solve problems, and assessment centers on the use of knowledge and proficiency of the science practices. Now take a moment with your team to consider your current state of instructional practice and your vision of what your classroom will look like in 3 years with respect to content. Press pause as you complete these activities. In a little while, we will investigate some resources that will help you plan the next steps. But first, let's examine the shifts in practice with respect to experimentation. Here is an online simulation that allows students to investigate with the motion of a pendulum. In a conventional science classroom, the teacher would provide the question, how does the period of the pendulum depend on the amplitude of the swing? And the teacher provides very detailed instructions for answering that question. The NGSS asks us to allow students to ask their own questions and plan their own investigations and develop their own models. So the teacher's role shifts from providing clear directions for collecting data and carrying out an investigation to providing clear directions for how to formulate a question and how to go about answering your own questions. In a conventional science classroom, teachers frequently assign reading at the beginning of the unit so that students have the opportunity to learn vocabulary and background information. Then at the end of the unit, students do a lab where they confirm what they already know. Now, we would like for students to do the activity first. Use this demo to have them generate questions about cloud formation and give them some time to do some investigating on their own. Then, students read the text in order to search for answers to their questions. So in summary, conventional science instruction begins with a unit on the scientific method. Hands-on science instruction is used to demonstrate facts of science and reinforce concept mastery. Clear directions are provided for experiments. But with our new standards, scientific investigations are designed not just to confirm what students already know, but to generate evidence and answer and inspire questions. Students should have the opportunity to invent and/or evaluate approaches to investigations. Revisions to investigative approaches and multiple attempts are routine. Take a few minutes with your team to consider your current state and vision with respect to experimentation. Jot down your thoughts on the planning tool. Please pause the video while you complete these activities. Now let's consider scientific models. Typically, models have been used in science classrooms to show students something, like this diagram of the interior of the Earth. With the NGSS, students will be given earthquake data, and they will create the model of the interior of the Earth from that data, just the way scientists do. Again, instead of being given a model of a caterpillar like this diagram, students will create their own model based on their observations. In another example, in conventional science classrooms, teachers provide formulas and students use those formulas to get new answers. With the new standards, students will make some observations, and from those observations, the students will generate graphical and mathematical models to represent the motion, and then they will apply these models to new situations. In summary, in conventional science classrooms, physical models are the main type explored by students, and they're used to help conceive of scientific ideas. Mathematical formulas are used to find answers. With our new standards, models will be designed and used to generate evidence, test ideas, and make predictions. And students will have the opportunity to build mathematical models. With your group, consider your current state and vision with respect to scientific models. Please pause the video as you complete these activities. Now let's talk about social interactions. In conventional classrooms, students are frequently placed in groups according to the need to share equipment. If you have 4 microscopes and 8 students, then you need to make groups of 2. With the NGSS, students must interact and construct meaning together. They need significant time dedicated to engaging in argument from evidence. They need time to evaluate different sides of an argument together. Here's some examples of student work that they created as they constructed meaning together. Students will need opportunities for productive struggle and discourse. They need to figure things out together without being told. In a typical chemistry classroom, students are provided with a set of rules. If you have a metal and a non-metal, this is how you name the compound. If you have two non-metals, this is how you name the compound. But why not provide them with a periodic table and these two tables and see if they can figure out the rules themselves? This type of social interaction is vital. Students will have to work together to figure out the patterns and generalize them. So in summary, in a conventional classroom, group work is used to manage logistical challenges such as the need to share materials. Cooperative learning occurs to help with student motivation while mastering content. With the shifts in practice, productive social interactions center on evidence, arguments, and discourse. Norms of discussion are established, practiced, and necessary to support a classroom culture centered on student learning. Take some time with your group to consider your current state of science instructional practice with respect to social interaction and what your classrooms will look like in 3 years. This diagram summarizes what we've been talking about. The practice of science, the way scientists do it, requires the ability to work in 3 spaces: investigating, evaluating, and developing explanations and solutions. The problem with conventional inquiry methods of teaching science is that too much time is spent on the left-hand side of this diagram and not enough on the right. We need to ensure that we focus on the minds-on practices of science, like reasoning and planning, and not solely on the hands-on practices, like observing and measuring. We need to do all of these things. And now, the most important part, how to achieve this vision. Take some time as a team to explore the resources outlined on the Resources for NGSS handout. You will need a computer so you can investigate the different web resources. As you look, consider professional development, your school's daily schedule. Is there time allocated to do science in a meaningful way? Are there ways to overlap science with ELA or math? Resources. Do you have Title I funds that can help make science accessible for all students? Will you need to purchase additional lab equipment? And a timeline for making these changes. On your planning tool, complete the steps to get there column for each of the 4 shifts in practice. Press pause as you complete these activities. As you consider your timelines, at some point you will likely need to make some shifts in curriculum. There's still a great deal of information that we don't know, especially with respect to large-scale assessments, so waiting to make curricular shifts until MDE has the chance to make some decisions is probably a good idea. For elementary school, the writers of the NGSS were very intentional about what content is learned at certain grade levels. Take a look at the NGSS website and view the standards by topics. You will see that there are 3 or 4 units per grade level. Each of these units has a page that articulates the performance expectations, 3 dimensions, and connections to other content and the Common Core. These pages are not intended to be curriculum documents. Remember, they explain what students will know and be able to do at the end of a unit. Teachers, schools, and districts will have to determine what learning experiences students need in order to meet these expectations. Secondary curricular shifts will be a little bit trickier. If you go back to the NGSS website, Appendix K outlines some model course maps for secondary science. The Michigan Department of Education has an internal team working on this too, but they have not yet published their recommendations. Please stay tuned to the MDE website for more information about course mapping that is aligned with the NGSS and whatever large-scale assessment Michigan will be using in the future. In closing, take a moment to reflect on your first steps. As you consider your school or district, what are some new ways you might support your students in being scientists?